Number one, so what we want to look at here is the graphing of potential energy versus displacement. And when we do the graph of energy versus displacement, the slopes in the line will actually give us a negative force. Or if you put that negative on the other side, force is the negative derivative of du over dx. The curve they give you here is for a mass on a spring. So if you look at the mass on a spring, the spring has no potential energy when we are at the bottom of the curve right here. The spring has lots of potential energy at the two peaks as it gets to a very far stretch. If you graph the energy versus displacement, it is a parabola. A positive parabola when you have positive displacement, and the curve goes on the negative displacement, still giving you positive energy. Either way you displace it because x is squared. So if you wanted to look at the forces involved, we have to look at the slopes, or the derivatives of each side. So the slope at the bottom here is flat. With flat slope, that means there is zero force. If I look on the positive x direction, and if I look at my slope there, the slope is trying to push the object back towards that 0 point, back to its lowest form of energy. So this is another way of showing a conservative force. The spring is trying to bring it back to lower potential energy. So there's where the force is. Yes, that might be a positive slope there. However, the derivative is a negative derivative, so the force points in the opposite direction. Here, I have a negative slope, but since it's a negative derivative again, the force points inwards towards that low energy spot, and the spring is always going to try and bring it back to a lower energy state. So the slope of a energy versus position graph gives us the negative force, the force that's trying to restore it back to a low energy point. So if energy is 1/2 kx squared, taking the derivative of that with respect to position gives you back the force that's involved, which is negative kx. So there's a couple of locations that we want to focus on when we're talking about potential energy curves. Let's talk about if an equilibrium is stable, unstable, or neutral. When it's stable, that restoring force always tries to bring it back to that equilibrium point. So like we saw in this one, the forces were always trying to drive it back down, drive it down to that location at the bottom of the graph. If I'm talking about an unstable equilibrium, any small displacements will accelerate you away from the equilibrium point. So it'll push it away from places where forces are zero and try to get you to lower energy as quickly as possible. And a neutral equilibrium is when you have any displacements but you don't change your potential energy whatsoever. So if I slide the iPad across the desk, I'm keeping the iPad at the same displacement, at the same height, and the potential energy doesn't change no matter which way I push it on the desk. Like we said before, our life is lazy. We want to be to our lowest energy state possible, so objects will always try to decrease their potential energy as quickly as they can in whatever direction they can. So looking at these curves here, the unstable equilibrium would be this curve, due to the fact that if you go from a location where there is no slope means zero force. That's our equilibrium position. We have zero net force on the object. But if I move either way, positive or negative, on that curve, I see that the force is going to push me away from equilibrium. This is a negative slope. The negative times negative gives me a positive force. And the opposite happens over here, forcing the object away from the equilibrium place. So that is an unstable equilibrium. In the first curve up here, pretty much between this region, the equilibrium is nice and neutral. The energy doesn't change much. However, it becomes unstable on the left side and still unstable on the right side. So all of them are going, no matter which way you put the object, you can see that it's going to try to accelerate away from equilibrium. The way that I remember equilibrium is I think of these potential energy curves as bowls. If I look at a stable equilibrium, imagine putting a marble in that bowl. And if I release the marble, that marble is going to roll down and back and eventually try to get to its lowest energy state possible. And if it stays in the bowl, then we call it a stable equilibrium. If I flip the bowl over and put the marble on top, no matter which way it goes, it's going to try to accelerate down towards the ground. It's never going to find a reason to roll back up the bowl to that equilibrium point. You can see these potential energy curves as wells or bowls that hold all the possible energy an object has. So when we look at an energy curve here, we could have that dashed line be the total energy of the system, and this looks like a stable equilibrium because if I put a marble into the bowl right here at that location, it has the maximum amount of potential energy it could possibly have. Say this energy here was 15 joules. At that location, the potential energy is 15, and as it moves down to this location, my potential energy decreases. So my potential energy might be 8 joules at this point. If my potential energy is lower at this particular location, due to conservation of energy, I've got to have the same amount of total energy. So that means that at that location, the object has to have 7 joules of kinetic. And if I know the amount of kinetic energy it has, I can also solve for its speed. As an object rolls through this curve here, you can track and watch the energy score and make sure it always matches up to what that total line is near the top. We'll do a couple other examples of energy curves in class to show you or highlight this example. And the last note here is that energy is conserved, like we've seen with our LOL diagrams and our energy bar graphs. That the total amount of energy of a system cannot change. The famous quote is that energy cannot be created or destroyed, it just transfers from one location to the next. So the things in our system could be all the mechanical energy like potential, elastic, kinetic energy, thermal energy due to heat from friction. If there was chemical combustion energy from chemistry, like if you're dealing with a rocket, there is stored energy in chemical bonds. So when you're dealing with that, all the energy of a system must be accounted for and must transfer. Now your system doesn't have to include the things that take away or add in energy, and you can show that on your diagrams as energy leaving the system or coming into the system. So the change in thermal energy there is the work done by friction. So if you do lose any energy from mechanical systems in our problems, you can most likely say that the negative work was done by friction, drag forces, whatever that force that's taking energy out of our system. So you want to keep score, make sure you track all the energies at each point, and you'll be able to solve for whatever variables are unknown if you just focus on energies at location A and location B. So if we want to look at an example of using an energy displacement curve, we can use this to answer some of the following questions, like using this, let's find the force for different locations on this curve. So if I want to find the force is the negative derivative of energy with position. So if I look at my first little segment here, I can see that I'm going from 4 joules of energy over 1 meter of displacement. So my slope there is 4 over 1. However, since it is a negative derivative, I'm going to get a positive amount of force. So the force for the first segment here is 4 newtons. And just to double check for yourself, remember that energy in terms of units is in joules or newton meters. If you're dividing that by a meter, you get back force. So just showing you some unit analysis on that one. So you're going to do that for each segment there. Find the force for each one and graph it. What I mean by graph it is graph out the force versus position and figure out where the force is during each little displacement here. So if I look at that force, so for the first meter, the force was a constant positive 4. If I look at the next, looks like my force is a slope of positive 1, or since it is the negative derivative, it's actually negative 1. Then it goes to positive 1. Then it goes to a negative 2. And then a flat line for the rest of it, so there's 0 force after that. So if you look at each segment, here would be the graph of my force over those displacements. When is the force to the right and when is it to the left? Well, it's to the right anytime we have negative slopes. So you can see that the force is to the right during those two segments, the first meter and the second and the third meter. The force is to the left on these segments. And up here, the force is 0. Now let's talk about that particle having total energy of 1.5 joules. Let's talk about its motion. If we want to talk about the motion of an object that has a total energy of 1.5 joules, what I told you to remember is that we could basically make a little marble and put that inside our potential energy graph here. If you look, if I'm at around the half-meter mark, I have 1.5 joules of potential energy. It can accelerate down and go up this slope, and the highest it can ever rise, as long as there's no friction, is back to the 1.5 joule mark. So it can make it to this location and the start point. Those are the two places that the marble can reach based on the total energy it has. The object only having 1.5 joules of energy, I would say that this is in a stable equilibrium. The reason is, on either side of the hill, the forces are pointing inwards and trying to bring it down to a lower energy state. It can never leave that little potential well. So in part D, this moment, saying, hey, what if you were going along, traveling to the left with a total energy of 1.5 joules? That's absolutely legal. It can do that. It can move to the left and go all the way up to that half-meter mark. What happens if another particle collides with it and adds an extra 1 joule of energy to that marble? What will it do? Well, on its own, without that extra joule of energy, it could get back up to this 1.5 meter mark, or this half-meter mark, but now that it's got an extra joule of energy, it can go all the way up to 2.5 meters. It can reach up to this location. And if my total energy now is 2.5 joules, well, if I track the marble on its way back, the marble can come down, go across all that, and it actually does have enough energy to leave the system and to leave that little potential well that we had. So with that extra joule of energy, it now can use that energy to leave. And anytime our potential energy decreases on this curve, following conservation of energy, kinetic energy must go up. So that's how you can kind of use a potential energy curve to discuss forces involved and the motion of objects just by looking at a graph.